Good morning, everybody, and thank you very much for giving me this opportunity to share some excitements about impact craters, which I have been always fascinated since my undergrads. So I work on impact craters with Dr. Adur sir. Um, we had some field trips in Lunar, and which triggered a lot of interest in me to study it. And even I did geology I took geology as one of the subjects. So currently I don't work on these impact craters as geological processes. I am a space scientist. I work on space weather and solar sun earth interaction mainly, but still it fascinates me this topic. So I will be just sharing some very basic stuff about what I understand, and of course anybody can add in that if something is needed in that thing. So I will be just focusing on mainly impact craters. So, and how they form, what type of formation they have. So I will begin here. So this is how, sorry, anything? Fine. So this is how the flow of a talk I have. So we'll be talking about what is impact crater, then what are the sources for these impact craters, and how where do we see them? So what type of how do we classify? Do we see different type of craters here? And then what are the evolutionary stages? Generally, what type of how the crater is formed after the impact of asteroid or something, and what are the significance to solar system exploration? And my job is little easy because last point is already taken care of, and some parts of the talk by Dr. Bhandari and Prajakta. She is exclusively working on early solar system. So I will be just briefly just touching those topics. So actually, what is impact crater? First, layman definition or even simple definition, if you want to talk about, it's nothing but a depression on a planet or any satellite or even asteroid. That depression can happen, and that was be caused by the impact of some celestial objects like meteorites or asteroids or comets. And those can be present on any other planet, rocky planet in the solar system, or even outside the solar system, as Prajakta mentioned, exoplanetary system. Even there, this impact craters would be forming, of course. So they are actually discovered or seen these extraterrestrial craters by Galileo, who pointed first time his telescope to the sky, and he saw that okay, there are some pits and some like depression type structure, like you can see here on the moon. This crater is exaggerated a little bit to maybe point okay, there is something structure exists on the moon. So from there we can say started observing these craters outside the solar, means outside the Earth also. And after that, this Schotter astronomer who actually used this term crater in 1791, and now it is very well known term impact crater, so volcanic crater we talk. So initially, there were like ambiguity about the moon. Most of the planetary scientists thought this all the craters are due to the volcanic eruptions on the moon. So it took some time to digest the idea that these craters are formed from the meteorites or asteroid impacts. And as we studied more, more differences evolve, how they are different than volcanic. And it is established like there are many craters on the moon which are in fact origin. And of course, on the Earth also some we have found up to now. So this is like first crater on the Earth which has been studied actually and confirmed, which is a impact origin or meteoritic or origin from the space by Barringer. And this is a panoramic view. I was fortunate to be here, so I took this panorama of a Barringer crater when I visited Arizona. And it's a very beautiful structure, well preserved, nicely shutters. You can see shattered rocks, and even still now people find there are some fragments of meteorites, and I do have some meteor fragments from there. So after this Barringer, this is just around 1 kilometer diameter crater, and it is in almost a deserted area. So not much erosion is there, water or something. So very nicely preserved and not very old crater, tens of thousands of years, something we can talk about. So what are these? These depressions are huge, like 1 kilometer. Sometimes they are smaller or very hundreds of kilometers. They can go in a size. And what are the sources of these then impact craters? Actually, they form due to the asteroids, comets, or meteorites. These are the main sources which are coming from the space and impacting the planet. Fortunately, Earth has some atmosphere, thick atmosphere, which filter out a lot of small objects, or even a bigger object gets scattered or decelerated. So somewhat it reduces their impact. These are the main formation sources for this type of structure of extraterrestrial objects. So how, like, this is a very nice view. I like this because you can really appreciate we are sitting in a danger zone always, no, not only other planets, but even Earth. Look at, this is a Earth orbit, this Mercury center at the sun is sitting, and there are like different like mesh of orbits. So they are not up to the scale, but okay, to emphasize, there are a lot of asteroids orbits that are crossing Earth's orbit also multiple times, and there is always, we live in the probability big chunk of rock just get attracted by Earth's gravity and impacts the terrain. So we are living in always this risk zone, no matter whether we accept that or not, or we realize every day. So I will go away about the showing the very beautiful scenarios or craters, impact craters. As I said, they are present everywhere in the solar system, wherever the rocky planets are there. So this is a Mercury photo. So you can see it is not very smooth surface. Small structures exist and grainy. So that is because of Mercury doesn't have atmosphere, and it is directly impacted by the meteorites or asteroids even in early solar system when it was forming. So these craters we do see as it is now also, it resembles very much our moon. You can see here moon craters, and Mercury and moon resemble very much because they are airless bodies, of course, that's why. And there is no weathering process, so we do see they are intact in millions of years. They have not disappeared from the surface, these craters. And even we don't see the Venus very nicely because it has a very thick atmosphere, like 90 times the Earth's atmosphere pressure. It is very thick and always densely with a dense clouds. But even Venus do have craters. So we do see some very complicated craters by imaging them with radio waves or microwaves. And we do see this complex ring type structures and some more morphological structure of the crater. So even in solar system, other than the Earth, we have Mercury, Venus, Moon, and even Mars do have a crater. So you do see very beautiful sharp feature here on the Mars. Mars do have atmosphere, so there is a slight weathering process happening there, but still compared to Earth is in a better condition. So we do see these craters well preserved. And as I said, sometimes even predator can be, so hunter can become predator like that. Even asteroids, even they do have also craters. The asteroid, if they hit Earth, they produce the crater or other planets. But even asteroids, you can see small pits or small structures which are craters, because even asteroid they collide with other, or some small chunks of asteroid, after collision they hit other asteroids and they form the crater. So the craters exist everywhere wherever there is a solid objects, and we do observe in the solar system. So I will just go ahead and talk about a little bit Earth. So you see here, like we do see like global map of the impact craters, and there are unexposed craters and exposed craters. As I said, Earth is like a very dynamic object. Living Earth is a living organism. You can see because we have a weather, we have now monsoon or rains, and lot of dynamic things are happening on the surface. So they cause the erosion. So there are a lot of craters, number of craters which are underneath. They are unexposed to the surface, and there are many exposed to the surface. So one can understand the difficulty why we don't see so nice picture of the Earth, cratered picture like Moon or Mercury, because of this weathering processes. So there are more than hundreds of craters now we have, and varying from few kilometer to hundreds of kilometer diameter of these craters we do see. And here in India also, as mentioned, there are two craters which are mapped here, which are confirm their impact origin. So, so why don't we see these craters on the earth? As I said, so this is a simple animation which will depict what happens. So this is Mars, Earth, and Moon, and look at the scenario. Because of weathering, we do see this when crater forms, this depression get filled with soil because of water and airflow or winds. They just fill this crater and they become almost flat compared to Mars or Moon, and that's why they are some very difficult to identify on the Earth. So it needs extra study, extra investigation to confirm whether they are impact origin or not. Oops. How do okay, yeah. So as we look at the craters, so they look very nice in images. And if you observe them carefully, you will start looking. There are a variety of craters. Sometimes very simple depression, like a very circular in nature, bowl type structure we do see, and perfect rims we see very clearly. So these are called as simple type craters, and we do have another complex crater. They could be very, very complex in nature. So the simple craters generally, when you observe on the moon or Mercury, you will see they are smaller in size, generally on the moon around 15 kilometers less, and on Earth generally they should be less than 6 kilometers in size, the simple craters. Smoothing surface and very sharp edges, circular. That is what is characteristics. So you can understand they are small or less energetic impacts. Generally, they are caused by that. But whereas you look at the complex craters, they have they are larger in size, sometimes 20 kilometer or hundreds of kilometer in size. On the Earth, generally greater than 6 kilometer in size, they become a complex in nature because they get you can see at the center there is a peak type structure, and these rings also become as like a concentric rings. You do see complex rings also, and the bottom, instead of like bowl type shape, it become a very flat in nature. So this bottom becomes very flat because of the formation process, and lot of rings you can have. So that is what a complex crater is formed. So generally, we can tentatively classify these two ways. More morphological classification is possible, and the geologists do that, or planetary geologists do that for the study. So this is what, just suppose you fly a drone or yourself fly on the terrain on the moon or something, and you will see how the crater should look, like a simple crater. So this is a beautiful view of the crater. You will see from the space if you are flying on the moon or you have a drone. Okay, so just go ahead. Oops. Oh, okay. Yeah. So these are the craters once again from the moon images. So look at the complexity involved in the crater, and look at the multi-ring crater. So multi-ring craters are very gigantic impacts, hundreds or thousands of kilometers in size. They can range, and they are most catastrophic events, even maybe in solar system experienced in early time, because those size of impacts were prominent when solar system was young, and well, collisions were very frequent. So this size we don't see now. This like 2000s of kilometer diameter craters forming. Fortunately, we don't want to see, at least on the Earth. Um, so this next I will talk about what now you look at. There are a variety of shapes and sizes of crater. From, I will say, it can go from micro size to kilometer size, because you have a small grain of meteor, and hitting in a space somewhere, it can form small pits or craters. So the size varies very drastically in orders of magnitude, and they are because mainly this depends upon the impacting object, which we call as a projectile. So what is the mass of this projectile and size of the projectile matters a lot. Bigger the size, bigger the impact, or bigger the crater we can have formed, or more massive it is, more kinetic energy it has. So how much energy is involved, actually, that is important in a crater formation. What is the kinetic energy of the projectile? So density and composition of the projectile, because that also determine a lot of dynamics. What is the density? So and a composition of the projectile, how hard it is, what is the melting point of the impactor, that also matter. But anyway, when the impact, the temperature goes very high. The velocity of the projectile, as I said, kinetic energy, so mass into velocity, mass and v square product. So these two play a very high role, and the velocities of these projectiles or objects entering the earth range in tens of kilometers, which is very, very fast, as Mandari sir also mentioned, like tens of kilometers per second, which is equivalent of like like 3600 second in a 1 hour. So you can calculate into 10, at least if you do, it's like a 36,000 kilometer per hour. So you can imagine how fast the object from the space coming and impacting the earth. So energy is very high. Then not only the impactor, like even the target material or to the surface which it is hitting, whether it is like a sand or a desert or like a sedimentary rock, or we have like a basalt in Maharashtra or Deccan Trap, whatever, it's very hard. So whether what is the hardness or what type of geology of the terrain it matters a lot in the formation of the craters and shape and size of the crater. So angle of impact, which is also underestimated sometimes, but if vertically coming down, then it can form very high impact. And when projectile is coming in an inclined manner, it forms a oval type, or shape is distorted of the crater. And last, I will say one of the crucial parameter is a planet's or satellite's gravity. So how strong is the gravity, that determines the later stages after the impact, how the crater unfolds on the planetary surface. So defines the parameter. So I will just show this. What are the average velocities of asteroids are generally do we see? So where we are in the solar system, that matters a lot. Like where you are at Mars, or you are at the Moon, or you are at Earth or Venus, because that determines what is the velocity of asteroid or meteorite will be hitting the planetary surface. So because even mass of the sun in come picture, as you go towards the Mercury, not only Mercury's gravity, but sun's gravity becomes very strong. So you can see as you go going towards the sun, the average impact velocity keeps increasing, because sun's gravity is pulling these objects towards the center of the sun, and that accelerate them. And so Mercury will having very high energetic or high velocity impacts on the surface compared to Earth or Mars. So similarly, as I mentioned already, so kinetic energy plays the role. So look at this graph. Here you have a final crater diameter in a meters. So just divide by 1,000, you will see in a kilometer. So 50 kilometer, 100 kilometer, 150 kilometer, or something on y-axis. And here you have a kinetic energy. And there are two, like Mars and Earth, we are showing here. So for Mars, you can see the diameters are very large, because gravity is also low on the Mars. That plays a role. The diameter of the crater goes inversely. And if our Earth, you can see how it is changing. More higher the kinetic energy, larger the crater, but that doesn't go very linearly. It gets slowly saturated for a higher kinetic energy. So from based on that, we can have idea how the energy is important for determining the size of the crater. And even here, you can see how the planetary gravity, this plot explains how the planetary gravity plays the role. So you look at the moon or smaller objects, they have a smaller gravity, And then that's why we can have very large craters, and that's why in the moon, on the moon, you can see hundreds of kilometer or thousands of kilometer size of the craters are very easily you can see them. But whereas the Mars, the size reduces this diameter of the crater just tens of kilometer, and when Earth you come, that also largest changes very small. But of course, there are bigger crater we do see, because sometimes we do have a big object coming and impacting even Earth, so that can form a hundreds of kilometer size of the crater. Yeah, so these are the formation stages typical, when crater fall, like as I said, so dynamics we'll be talking, like how the impact happens. And this is very complex. As we feel it is very simple, just one object you throw on the terrain and you'll form some pit, but it is not like that. It's very complex. And the problem is that we cannot actually simulate in actually real environment these conditions on the Earth. Some small scale we can always do, but scaling is always an issue. Because these crater sizes are few kilometer in size, and energy involves are in TNTs. So conditions are very different. But whatever we understand, whatever observation we do based on the moon observation or craters on the Mars or Venus and our own Earth, based on that we have tried to understand how the crater is forming, because they have a different stages. Like you look at here, oops, sorry. Okay, so you look at this. This is a simple crater. This is the right one. Left one is for a simple crater, how it forms, and next right one is for a complex crater. So first is a contact and compression phase, and then excavation phase and modification phase. So these are broadly described like when impactor just touches the ground or target. That is called contact and compression phase, which very short lived, and then excavation phase where because of contact this melts and comes out everything, and then modification stage with geological processes takes place, collapsing and all. So we'll just briefly look at them in detail, just small details, not, I don't want to burden more on this. So this is what a contact and compression phase technically looks like. Don't get lost in this picture. This is a simple picture. Like this figure shows this is an impactor or an asteroid, something hitting on the ground, and these lines are showing the pressure. So look at the pressure values. They are ranging few hundred gigapascal. And this is a scale of 0 to 50 kilometer size, you can understand. So around 50 kilometer projectile is hitting the ground, you can assume that, and how it is going to react to the ground. And the pressure involved, as I said, around few hundred gigapascal. And that pressure, if you convert into in terms of the Earth's atmospheric pressure, it will be like million times Earth's atmospheric pressure. So the enormous crushing is happening at this contact point, and that triggers the shock wave because this impact, when it hit is moving greater than the speed of light, speed of sound in the target material, and that shock wave. Shock waves propagate inside target material, and when shock waves are going through this target material, they heat the whole target like ground and melt it, vaporize it. So a lot of plumes are ejected from this cavity. And you can understand now 0 to 50 kilometer was this size, and at this later size 0 to 50 is this. So look at this scale, this huge compared to the target. So well, if even your target is just 50, impactor is just 50 kilometer in size, your crater could be few hundreds kilometer, thousands of kilometer in size, because the energy it liberates at the contact point is a huge, compared like more than atomic explosions we do see. So this is next stage happen at the we have excavation phase, where this also is very short lived. This is happening in a blinks of eye, like first like contact and compression is less than a second, very fast. And whereas this excavation phase, that is around tens of seconds, or it can change in few minutes depending upon which where the crater is forming on the moon or Earth or other planet. But this is also very fast. In this you can see this as it is vaporize the whole terrain, and there is a ejecta. This target material get ejected because kinetic energy is transferred to the bedrock, and some particles get ejected in the atmosphere, and they fly away from the crater and deposit few kilometers away from it. So that's how the basically this crater, main crater, transient crater, what is formed during this excavation phase. And if you go ahead, you look at the modification phase, which is a later stage after the excavation phase. And even this also lasts like a very small, like few minutes in time scales. So we do have a crater depression like this looking. So true crater or transient crater, what we feel is like this. But after the modification phases, these walls collapse, debris fall into the crater, and they deposit whatever plume has gone, that also condense and fall, and they deposit inside the crater. And the apparent crater, what we actually perceive, is less deeper than actual crater. So that is also a problem. Like we feel okay, crater is not very deep, but actual original crater has formed very deeper. And depending upon the impact velocity, size, we may see this whole impact meteorite got completely vaporized and lost. We cannot see any traces, or sometimes it's possible some fragments or some part of the meteorite gets say survive, and you can see in deep down in the crater somewhere sitting that object, but that happens rarely. So this is now, as I told you, we do observe, and there are like one experiments in a lab we can perform. So even when I was looking at this crater, we did actually those experiments at home. We used some projectiles and put fire them on this sand and try to understand how they behave. So actually, as I say, this is not simple what we look at, because these are very small velocity impact, small scale, and we are studying in the lab. But actual impact is very complicated because the velocities and energy is very high, and they actually impactor and ground melts instantaneously because the temperature reaches around tens or 20,000 Kelvin, which is very, very large. And that time, they do no longer act like a solid objects. It's like a fluid completely. So that physics is very different as we study in the lab. But at least one can notice from these images, you can see in a millisecond time frame how fast this is happening. So initially, the size of this crater or depression is the same as the impactor, but at later you will see impactor is very small, the crater size is very large. So similar analog happens on the planets and actual impacts. So then now next is that how do we identify these craters? So people may be aware about there are like terrestrial volcanic craters also exist, and lunar impact craters do exist. And as I mentioned earlier, as astronomers or planetary geologists were puzzled whether lunar craters are volcanic or impact origin. So similarly, it's not very easy always to determine them on the Earth, at least because specifically weathering processes, but there are typical characteristics do volcanic and impact crater they distinguish. So simplest, you can see the profiles of this, like volcanic, like you do see elevated structure like rim, elevated terrain, and then like this. But whereas lunar crater are deeper compared to the base terrain. They go as a depression, not elevated and then depression. So that is one of the simplest, but that can become complicated, as I said, to distinguish sometime. So these are the few characteristics I just listed here. There are more one can use to really nail down whether this crater is an impact origin or not. So they generally appear like circular or oval in depression with a raised rims. That is one characteristic of the impact crater. The floor is lower than the surrounding terrain. Then inverted stratigraphy means the strata, how the deposits are formed on the geological terrain. They get inverted because we have impact and then ejecta falling from deeper first and then other side. So we do see inverted stratigraphy near the crater. That is very good indication. Then ejecta. So ejecta is nothing but this material excavated from the bowl-shaped crater and just spread near the crater. And the shock metamorphism in rock. That is very distinction this can be used, because the pressure involved is a few hundred gigapascal, and the rocks get modified, and terrain like minerals get new minerals get form or metamorphosed. So these signatures we can look at only, which is possible in gigapascal pressure conditions. Then the visible structures, you can see shatterstone, tektites, or some other minerals, and some melt type structures around the crater. So these are the some just samples how they do appear. So these are the shatter cones. They are formed due to the high velocity impact shock wave. So this as I mentioned, this generate a shock wave similar like supersonic planes going in the atmosphere. They do show the shock wave. Similarly, as a projectile is moving very fast compared to the sound wave in the target material, they form the shock waves, and the shock waves get radially outward, going away from the crater. So they put imprints on the crater, these rocks, and you do see the shatter cone type structures. Then we have a tektites already mentioned earlier in talk. So these are the tektites, nothing but a glass spherules. Like we have silicate minerals in the terrain, which get vaporized by this high temperature conditions, and they get once again condensed and they fall back on the ground. So look at this. This is a very black, and because they suddenly get chilled, and so they are like a glassy in nature. And since they are traveling in the Earth's atmosphere, they are forming aerodynamic shapes, like a very distinct, sometimes very beautiful shapes you can see. Even we did collected some tektite like spherules, grass spherules from the lunar with a dusser, and we studied them. Very beautiful structures and very abundant near the lunar at least we have observed. Then folded strata, as once again like completely bending happens near rims and all. So this is also one of the nicely observed near crater. And sometimes we do see one meteorites fragments like a Barringer crater. There are meteorites, small fragments still people can collect. So not everywhere we do see that, but some where it survives, impactor survives, because impactor could be like iron meteorite, chondrite, as already Prajakta mentioned. There are different types of meteorites and asteroids. So depending upon the composition, sometimes this iron meteorites may survive in this impact. So next beautiful stuff about the craters is ejecta. So what is ejecta? I mentioned already. So this is a crater, and you do see there is a different, like look at these images. If you compare all these images, there is a crater at the center, but white patches around them. And sometimes different, they are having a different morphology or shapes. And actually this is nothing but the crater and spreading nations. So here we see very symmetrical, almost you can say, or slightly asymmetric spread of this material from the bowl. Whereas here you don't see very highly asymmetric, like you do see here ejecta or material is falling here, but nothing is here. So that's like very strange why it is not happening then. And if you look at this crater, this is more weird. Like you do see only in one direction spread of this ejecta and nothing here. Okay, and if you look at this another crater, so you do see the like ejecta very symmetric, but they have a layers, first layer, second layer, or something. So this the material how it falls on the surface around the crater is a very interesting phenomena according to me, because that is not uniform, and lot of mechanics or lot of dynamics goes in what causes that. So here are like I'm just showing simple, like it could be very circularly uniform, sometimes off center, like crater is sitting there, but it is off center ejecta. Sometimes very highly elliptical ejecta we may see, and sometimes we do see some part no ejecta, only some part there is a. And here you do see like butterfly type ejecta, like wing type structure form, no ejecta falling here or on opposite 180 degree. So this has a lot of puzzling questions still. We don't understand exactly how they form, and some understanding we have gained, but a lot of parameters mostly like impact angle. How oblique is the impact? Like suppose perpendicular coming, so you will have a uniform mostly ejecta, but highly oblique impacts can form this type of butterfly, and very highly asymmetric impacts. So that's what we can look at this lunar craters where they are very well preserved ejecta and study dynamics. Then I will come to the Earth now. We have seen very beautiful pictures, but do we have on the Earth also these craters? Of course. And near Mumbai, from Mumbai, this is the closest crater we can have, like lunar impact crater. And look at this. This is satellite image. Very nice structure, bowl type structure. You can see rim wall and elevated structure from here. And actually, ejecta is spread in a nearby rim. But unfortunately, we have a lot of farming and there are villages sitting there, drainage system is there, so all this is has destroyed. It's like actually how it formed, but still the crater is very sharp because it formed in the basalt and it is not very old, so that is one advantage. So we can really study them because nearby it's within India and one of the unique craters to be formed in a basalt, which is very close analog for Martian studies. Suppose Mars crater we want to study, and this lunar is the closest. We cannot go to the Mars now and study the crater in situ, but lunar crater is possible for planetary geology. So that's one of the best bet we have to study this Martian analog just nearby. And a lot of studies has been conducted to confirm and study its dynamic. So once again, this is a view of crater, how it looks, nice rim around 2 kilometers in size. So it's a very gigantic. If you go there, is how beautiful it is. As soon as you walk and there's a V-type opening and you go there and you realize, oh, that's really vast crater. So another crater we have now Ramgarh, and there are many more in India which are still yet to be confirmed or on the way to get confirmation of impact origin. This is also a few kilometers in size and very complex crater, looks like bigger than the lunar crater. So as we say, how like what this cratering process? So these big craters, do we see today, tomorrow, how frequent they are? Or they have changed with time? That is very important question we should ask. Oh, these are like few thousand years or million years old craters we are talking about on the Earth or any on the moon. So why don't we see those frequently now? If you look at the moon, so many craters are there. So somebody will think, oh, we should see every day some crater forming somewhere. But okay, there is a reason we don't see them because how the solar system form, that also matter. So look at, this is a graph, like 0 is the current era, and as you go back 4 billion years back in the time, a rate of is coming. Yeah. So if you go back in the time, you will see number of crater formation was increasing. So there was a peak in the early solar system. Sorry.
Sorry, some disturbance. Go ahead.
Yeah. Okay. Yeah. So their number of craters the formation frequency was very large and it has decayed very largely. And that's why we don't see very frequently crater forming on the moon or Earth nearby. So the frequency has dropped down, and that gives a lot of clue about early solar system formation. Just looking at or determining the ages of the lunar crater, we can understand how the early solar system was, because on the moon they are very well preserved as compared to the Earth. So another, like what we can learn is how probable is this impact crater, because that has to deal with our survival also on the Earth, as sir also mentioned, Bhandari sir, like there are extinction events and luckily they are not very common. But look at this graph. So it talks about the number of crater frequency monthly, every year, or like up to hundreds of million years. And next axis, it talks about the energy. So ranging of few hundred TN to millions of TNT. Okay, so small craters are very like monthly you can form, every year you can form, very, very small energy involved in that. But look at that, like Tunguska type event once in a century, and that happens in megaton TNT. Okay, so those are also very huge events. We have not witnessed after that such big Tunguska type event. And then if you go to KT impact, like 65 million years back, asteroid impact, which really killed dinosaurs and lost a lot of life got extinct during that time. So those types of events are actually are a few thousand, 10,000s or millions of TNT energy involved, and those could be globally catastrophic, and they do happen in millions or yeah, tens or hundreds of millions in time, once in a tens or hundreds of million year, fortunately. And if such even happens, we are actually in danger or verge of extinction. So it is very important to know what is the frequency of such event, so we can actually prepare for that. And there are like a lot of by NASA, there is Asteroid Watch program which is trying to monitor a few like objects floating in the space, their size and their orbit, so that if something is approaching big, large enough to our search, we will be at least knowing, okay, it's coming, and do some mitigation, mitigation preparations. But still, we don't. I don't think we have a good enough technology to avoid a kilometer size of impacts at currently. So what we learn, like after looking at this like, so this is the last slide I want to end here with like saying what is the significance of this impact craters, why we should study. Of course, I hope that is conveyed already. So we can study the early solar system evolution, how our solar system evolved, and not only our solar system, how other exoplanetary solar system have evolved. We may get hints from that, which is very important for astronomical studies or planetary studies. And how does this cratering modify planetary surfaces? That is also very crucial. You know why? Because these asteroids, cometary impact bring lot of life origin or water from the space, and they shape the complete tectonics or geology of the planet. So that's why we need to study them. So, and this hypervelocity impact processes, as I said, we cannot perform them in lab because these are the huge few kilometer size and energy involved in millions of tons, very large impact craters. So they cannot be simulated in lab. Of course, simulation in computer you can do, but we need to learn from whatever evidences we have. So in situ measurements, in situ geological studies will help us to understand how they really form, what are the energy involved, because there are, like as I said, multiple multi-ring structure, and actually we really don't understand what causes these multi-ring structures in a so huge craters. What is the origin of that? Still we are puzzled about it. So, and how the life is formed due to these impacts, could be the seeds are in the impacts of asteroids from where we originated, and even those could be the reason life may end on the earth, like they can cause mass extinction. So it's very important to study the impact craters and how they form. Then places for frozen water outside. So this is one of the indirect importance, like the craters on the moon. There are like some big craters near polar region where always they are in shadow and sunlight doesn't reach. So these craters harbor the water in a frozen form. So those are the places we can hunt like or search the water signatures or something on other satellites or moon type objects. So, and already like Chandrayaan has done that, like have found the water on these polar regions that's hiding inside some craters. So then high pressure physics and mineralogy, that is one again like physics or science study we want to look at, like this type of conditions, hundreds of gigapascal, they originate only in this high impact, hyper velocity impact. And the mineralogy, we can study whatever minerals they form and what we expect on other planets or as a planetary geologist. So they have interest in that. So a lot of implications for solar system science and as a life concern. So I hope I conveyed this point, and I'll stop here. Thank you.
Thank you very much.